Hello, in this video I'll be talking about the steps to solve the questions in Unit 5 Worksheet 3. A metal rod of mass 0.33 kilograms lies across two parallel conducting rails that are a distance of 0.52 meters apart on a tabletop as shown in the top view. Here's the top view down below. A 3 ohm resistor is connected across the left ends of the rails. The rods and the rails have negligible resistance but significant friction with a coefficient of friction of 0.2. There is a magnetic field of 0.8 Tesla perpendicular to the plane of the tabletop. A string pulls the metal rod to the right with a constant speed of 1.8 meters per second. So what we see in a situation like this is that when we pull the rod, so here's the metal rod, when we pull that metal rod to the right, our flux increases. Remember that flux is magnetic field times the area times the cosine of the angle between them. And we're increasing the effective area, so we are increasing the flux. Now, just a note, if we increase the flux, in other words, if we essentially have more X's, so before we had these four, and as I drag this rod to the right, I'm increasing the flux. What's going to happen is that the loop of wire is going to create a current in it, and that current is going to create a magnetic field that opposes the existing flux. So opposing the existing flux is going to come out of the page. Now, in order to figure out the direction for that magnetic field, I would need to use a right-hand rule to figure out the direction of that magnetic field. And so, let's see. If I take my right hand and put it around the wire like this, my fingers would be coming out of the page inside the loop and going into the page outside the loop. And so that tells me the direction of the current. And actually you can do that anywhere on this loop. So if I had my hand upside down like this, I'd still have the current coming out of the page there. So I would have that the current is going counterclockwise in this scenario. Okay, I'm gonna erase my work there. And again, the flux is increasing in this scenario, and I just determined that therefore the current must be counterclockwise. That's not a question, but that is something that I want us to practice doing in this unit. Okay, so we figured out the direction of the current. Now let's figure out the magnitude of the current needed. What I'm going to do is use this formula, E equals BLV. This is EMF. And this equation works for specifically this scenario. I'm going to take the magnetic field, which is 0.8 Tesla. I'm going to take the length of the wire, which is 0.52 meters, and take the velocity, which is 1.8 meters per second, and I get 0.7488 volts. Then I would use Ohm's law, V equals IR, to get the current. So 0.7488 equals I times 3 ohms, and I comes out to be 0.2495 amps. Okay, so again, this first question hinges on an equation. That equation is derived from flux. The V is indicating that the area is changing, and remember that we need a changing flux in order to induce that EMF. Let's see. Let's try part B. Calculate the magnitude of the force required to pull the rod to the right with a constant speed. Okay, so the force, the magnetic force on a current carrying wire in a magnetic field is BIL. B is the external magnetic field, the one that is the X's in the picture. I is the current in the wire, and L is the length of the wire. So I've got the external magnetic field is 0.8. The current in the wire I just figured out, 0.2495 amps, and the length of the wire was 0.52 meters. And when I multiply that out, I get 1.04 newtons. Now that's the force that I would need to pull with if this were frictionless. And remember, you can't get something for nothing. To induce this current, we're going to have to do work. And the work we're going to have to do is a force times a distance. But there's more. There's also friction. So I'm going to have to figure out the force of kinetic friction, which in this case is mu times the normal force, or mu mg, because it's flat. Mu is 0.2. The mass is 0.33 kilograms, and then, of course, 9.81 meters per second squared. When I multiply that out, I get 6.47 newtons. Okay. Next up, these are callbacks to Unit 4. Calculate the energy dissipated in the resistor in 2 seconds. So power is equal to IV, but it's also equal to I squared R, and it's also equal to V squared over R. The form of this that I'm going to use is I squared R, because I have current and I have resistance. So the current was 0.2495, and the resistance was 3. When I multiply that out, I get 0.847, sorry, my bad, 0.187 watts. Oh, I just noticed here, I messed up. I didn't finish this answer before. I got the FK. I have to sum these to get the total force. So the sum of them is 0.751 newtons. Pardon me. Okay, so that's the power dissipated in the resistor. We know that power is energy over time. So energy is power times time. The time is 2 seconds. So we've got 0.187 watts. A watt is a joule per second times 2 seconds. When we multiply that out, we get 0.347 joules. Okay, calculate the work done by pulling this. Calculate the work done by the string pulling the rod in 2 seconds. Okay, so first of all, I can figure out the power. Power is work over time, or force times distance over time. Distance over time is velocity, so this is force times velocity. The force I determined above was 0.751 newtons. And the velocity that we're pulling the rod is 1.8 meters per second. So when we multiply that together, we get 1.35 watts. And then the work would be the power times the time, which would be 1.35 watts times 2 seconds, which would be 2.70 joules. Then finally, for part E, compare your answers to part C and D. Provide a physical explanation for why they're equal and unequal. So we had to do more work. 2.70 joules than was dissipated in the resistor, and the reason is friction. Friction accounts for the difference. We do 2.70 joules of work to pull the rod, but some is dissipated. It would be better actually 2.70 minus 0.347, whatever number that is. that would be the amount dissipated. Okay. I hope that made some sense. Let's try another one. These are both inexplicably numbered 27. Sorry about that. The diagram below shows a simple mass spectrograph. It consists of a source of ions, those are charged atoms, that are accelerated essentially from rest. Pardon me for a moment. By the voltage V, and enter a region containing a uniform magnetic field B. The polarity of V may be reversed so that both positively charged ions, cations, and negatively charged ions, anions, can be accelerated. Once the ions enter the magnetic field, they follow a semicircular path and strike the front wall of the spectrograph, on which photographic plates are constructed to record the impact. Okay, so this scenario is actually including concepts from Unit 3 and Unit 5. In Unit 3, we studied how voltage is two charged plates can have a voltage between them, and that, so let's say there's a voltage difference here, a potential difference, and so there's an electric field, and that electric field is going to make these charged particles accelerate. They will accelerate until they get to this point where they enter a magnetic field, and when they enter the magnetic field, they have a velocity, and then we would use either the right-hand rule or the left-hand rule to determine whether they curve to the left or the right. My fingers are going to point down into the page, and my thumb, so my fingers are the magnetic field, my thumb is the velocity of the charge, or the direction of the velocity of the charge, and my palm tells me the direction of the force. So for a positively charged object, I would use my right hand, and when I set it up, I can see that my palm is going to exert a force this way. And what's cool about this is this force points toward the center of the arc. That's a property of circular motion, that at any given point, the force and the velocity are perpendicular. The velocity is tangent to the arc and the force points in. So this would be a positive charge going that way, and the other one would be a negative charge. Okay, so let's do some calculations here. What is the acceleration of an ion of charge Q just before it enters the magnetic field? Okay, so the net force out here is due to the voltage. The net force is an electric force. And the electric force, again, is based on the charge and the electric field. And the electric field is the voltage divided by the distance between the plates. So I can make some substitutions here. I'm also going to substitute that net force is equal to mass times acceleration. So net force is equal to mass times acceleration. So I'm going to start with mass times acceleration equals electric force is QE, where E is V over D. So I can write QV over D. V in this case, again, is voltage. And now I'm going to solve for acceleration. Acceleration is QV over MD, where again, V is voltage. I'm going to put little serifs on it to indicate to myself that I'm talking about voltage there. Okay. Find the speed with which an ion of charge Q enters the magnetic field. So I'm going to assume that the initial velocity of this thing is 0. I'd like the final velocity. I have the acceleration from above, qv over md. And d, the delta x up here, the delta x is this d. Oops. So I can use a kinematic equation. So v squared equals v naught is 0, 2, the acceleration is q v over md, and then delta x is d. So then I would solve this for velocity, and I would get the square root of 2qv over m. All right, part C we already looked at. Which semicircular path would a cation follow? This is a positive charge. So a positive charge we figured out would follow path 1. Again, we're using the right-hand rule. And a negative charge would follow path 2. Let's look at part D. Determine the mass of a cation entering the apparatus in terms of y, q, b, and v. Okay, so back to this picture here. We are looking at circular motion, and we will recall that an object moving in a circular path has a force toward the center of the circle, and in this case, that centripetal force is the magnetic force on the charged particle. So I'm going to set up an equation setting magnetic force equal to Fc. So I'm going to say Fc equals magnetic force. So mv squared over r is going to equal qvb, where v is velocity in this equation. So if I simplify this equation, I cancel out 1v from both sides. I can say that mass is equal to qbr over v. So now what I'm going to do is substitute what I know. Excuse me. So the charge of the charged particle is Q. The magnetic field we're calling B. So I can leave those the same. The radius of this path is half of y. Y is the diameter. So I'm going to take y over 2, or 1/2 y. And the velocity we just figured out in the last part, it's the square root of 2qv, where v is voltage, over m. So I could simplify this to solve for m. I've got m on both sides of the equation. qby over 2 times the square root of q2, oopsie. So to solve this for m, I'm going to have to square both sides. When I square both sides, I'll get m squared equals q squared, b squared, y squared over 2 squared, and then times 2q voltage, and then the m on the bottom would come up to the top. And now, let's see, one of the m's cancels on each side of the equation, and now it's just a matter of simplifying. So I would get m equals q, this one q cancels, qb y squared over 8 times the voltage. Part E, once a cation charge Q enters the magnetic field, how long does it take to strike the photographic plate? Okay, to solve this, we are going to take velocity equals distance over time and rewrite it to say that time would equal distance over velocity. Now, the distance that the object travels is this semicircle, and the diameter of that semicircle is y, pardon me. So the distance is just pi times y over 2. And then the velocity we found earlier, the speed of the particle when it enters the field, is found from part B. So it's the square root of 2q times the voltage over m. So I can write that out as pi times y over 2 times the square root of 2q the voltage over m. And we certainly could simplify that, but I think that's good enough for now. Part F, what is the work done by the magnetic force in the spectrograph on a cation of charge Q? Okay, so what's happening here is we've got a magnetic field, got the charged particle entering the magnetic field perpendicular to the magnetic field, and then it exerts, so there's my velocity, and then the force is, for this charged particle, is going to be perpendicular to that velocity. So because force and velocity are perpendicular, the work is 0. Remember that work is equal to FD cosine theta. So if theta is 90 degrees, the cosine of 90 is 0, so no work would be done in that scenario. All right, let's look at our last example problem here. This is actually from the 2013 AP Physics B question number 6. And it says 2 long straight horizontal wires are near each other and parallel, with one directly above the other, as shown in the figure. Wire X is fixed in place and connected to a battery not shown. Okay, so I'm just going to put little dots to remind myself that that one is fixed in place. Wire Y, which is part of a second circuit, is free to move vertically. Okay, so wire Y can go up and down and is suspended at rest by the magnetic force between the wires. The mass per unit length of wire Y is 5.6 times 10 to the negative third kilograms per meter. Neglect effects from the parts of the circuits that are not shown. Okay, part A, calculate the magnitude of the magnetic field produced by wire X at the position of wire Y. Okay, so at this point, you should be able to use a right-hand rule to figure out the orientation of the magnetic field, assuming again that this is conventional current. And to get the magnitude of the magnetic field, the formula is the permittivity times the current over 2 pi r, where r is the radius of that circular magnetic field. So we've got 4 pi times 10 to the negative 7th. That value is given, that permittivity value. The current is 65 amps. And then 2 pi, and the radius is, let's see, this is 0.025 meters. That's our radius. So I'll plug that into a calculator, and I get 5.2 times 10 to the negative 4th Tesla. Okay, part B. Calculate the magnitude of current in wire Y. All right. So the magnitude, let's see. The magnitude of the wire in, or the magnitude of the current in wire Y is created by the magnetic field from the top wire. So here I've got this magnetic field, and It says that it's suspended at rest by the magnetic force between the wires, which means that if I were going to draw a force diagram for this wire, there would be a gravitational force down and then a magnetic force up, and that magnetic force would be caused by the attraction between the wires. That means that the current must be going in the same direction to cause an attraction. And let's go ahead and calculate the magnitude of the current that is required. So I'm going to use the formula for the magnetic force in a current carrying wire, F equals BIL. Now, one thing that you'll notice is they're giving us the mass per unit length. And the mass per unit length we could use to get the weight per unit length. So if I take F over L, that equals BI. F over L, again, is going to be weight per unit length, which is going to be 5.6 times 10 to the negative third kilograms per meter. I'm going to multiply that by 9.81 meters per second squared to change that to weight. And then the magnetic field, for wire, sorry everybody, this stuff is a little complicated. At the location of wire Y, the external magnetic field is caused by wire X. So the magnetic field caused by wire X is external to wire Y. So I'm using my answer from part A. And I'd be looking for the current. So now this is something that I can solve, and when I solve it, I get quite a large current. It's 105.6 amps. All right, for part 2, indicate the direction of the current in wire Y. It's definitely to the right because the wires are attracting. It says now wire Y is moved to a new position, so it's closer to wire X, but wire Y is still below wire X and is still carrying the same amount of current. Determine the initial motion of wire Y. So if I take, let's use a different color. If I take this wire Y and I move it up, what's going to happen is it's going to be in a stronger magnetic field from the top wire. So wire Y will accelerate upward toward X since the attractive F magnetic force will be greater than the gravitational force, since the wires are closer together. And remember that the that the magnetic field is bigger because the radius went down, so the magnetic field is going to go up. Okay, let's try part D. Suppose wire Y is moved to a new position 0.025 meters above wire X. What changes in current must occur to maintain equilibrium? So if we took the bottom wire Y and put it above, now it would need to repel. So the current would need to go in the opposite direction. So the direction of current must reverse. So that the wires repel. And the magnetic force is upward. Okay, part E. Oops, sorry, I lost my place here. With wire Y still above wire X, the circuit connected to wire Y is removed. Wire Y, which is 1.2 meters long, is then moved vertically up and away from wire X with a constant speed of 3 meters per second. Calculate the magnitude of the induced EMF in wire Y when the wires are 0.05 meters apart. Okay, so let me come down here and draw a picture. So now wire X is on the bottom. It still has a current of 65 amps. The distance between the wires is 0.05. I definitely need the strength of the magnetic field at this point at wire Y. And to get that, I'm going to use the formula B equals permittivity times current over 2 pi r. So that's 4 times 10 to the negative 7th. I'm sorry, 4 pi times 10 to the negative 7th. Times 65 amps over 2 pi times 0.05. So that's 2.6 times 10 to the negative 4th Tesla. That's the B field right at that point. Then to get the induced EMF, the induced EMF is equal to BLV. So this is the formula for the induced EMF in a wire moving in a magnetic field. So that's going to be 2.6 times 10 to the negative 4th times the length of the wire, 1.2 meters, times the speed, which is 3 meters per second. So all of that was given here. And when we compute that, we get 9.36 times 10 to the negative 4th volts. Okay, part 2, indicate which end of wire Y is at a higher electric potential, and justify your answer. So the answer is the left end. So in order to let's see, to move this, let me make sure I'm doing this right here. Okay, so this wire is being moved vertically up and away. So we're going to have to do work to do that. In order to do work, the force of wire X on wire Y and the force of wire Y on electric potential. So just to sum up what I've got here, I know that in order for me to have to do work on this wire, there must be attractive forces. The force of X on Y must be toward the force of Y on X. And I know that two wires attract when the currents are in the same direction. So the current is going from left to right. And I know that current goes from high potential to low potential. If I added the other wires, or if I added the rest of this circuit, this would be the positive terminal and the current would be coming around like that. Okay, I hope that makes sense.